Hello everyone. Today I wanted to cover the last part of the YODA paper, which is on implementation and experiments. And the first thing that might come to your mind is, why do we have to do implementation and experiments? We have some very good ideas. We've done some theory. We've considered different security models like honest plus Byzantine, quasi-honest plus Byzantine. We proved various results. Even for the miracle algorithm, we've theoretically proved certain optimality results and so on, right? So why do we have to do an implementation and and experiments? Now these top conferences in security, like NDSS, where we publish the work, but also the other ones like CCS and so on, they expect some implementation and experiments. And again, we must ask why. Why are they so insistent? Because if there are good ideas, why not accept them? So we should also think, why did Satoshi implement Bitcoin? Because Satoshi came out with his white paper sometime at the end of 2008, and in early 2009 he came out with his implementation. So it should be obvious that Satoshi didn't do his implementation actually just between the white paper and the code coming out, because that was a very short time of, let's say, a few months. He must have spent a very long time, maybe years together, fine-tuning Bitcoin, because as we've seen in the previous course, Bitcoin is a very advanced idea, and it's very finely optimized. The UTXO model and the code that is used, the stack-based language and so on, right? And optimizations using Merkle trees and so on, so forth, right? So it's a very highly optimized thing. What is the interarrival time between blocks? Everything has been thought about. And many of those insights would have come through actually by building and implementing Bitcoin. Okay, it's very hard to just come up with an idea and then come up with something as good as Bitcoin. Right? So actually doing an implementation and experiments not only gives a reader of the work some confidence that this will actually work in practice, but it also gives us some insight into what might be some practical issues that we might face, right? So I'll just write down a few of those things. So why do an implementation? Well, because first of all, real world conditions are not always considered by theory. So it's hard for somebody to consider too many real world conditions while doing theory. They would always simplify things. For example, in Satoshi's double spend attack, he had assumed 0 delays, and we know that that's not true in practice, right? And it took many years for people to advance that theory which Satoshi had come up with, to take into account delays. Right, as recently as December 2020, there have been papers coming out on security of Bitcoin, right? So it's hard, but taking into account things like real world delays, right? And so it's hard to do theory which is very general enough, right? But if you do an implementation and test it out, you can actually see what happens in under real conditions, right? So there could be unexpected phenomena which we would not have anticipated. Right? And we'll see from some of the experiments we did for YODA what we found out. Right? Certain things, if you think hard enough, of course, you might be able to realize that they would occur, but we realized them after doing the implementation. Okay? Okay, so it also it gives confidence to people that the idea will work. So you may have, like, say, a startup idea for something, and you might want funding, right? And somebody has put in a lot of effort to earn, his money, and he wants to invest in your company. So he wants to have a good idea that what ideas you have will actually work in practice, right? Because he doesn't want to put his hard-earned money, in some place which is too risky, right? So always when people do startups, they will come up with some sort of a prototype and say, here, you see this thing, this idea of mine actually works. And so then, then maybe the people are more free to actually give some funding and so on, right? So, so what did we study in our experiments? So our students, the student authors of the paper, Saurabh Das and Abhijit Anand, they did this implementation on Ethereum. So they took the Ethereum code and they modified it. Okay, so they had to maybe come up with their own smart contracts which sort of did what YODA was supposed to do, at least mimic the main functionality, right? And they had to have a big emulated system of several machines. They used several different machines. I think we used around 16 or a large number of machines, right, in our lab in order to test a large network, right? So what were the quantities we studied? So first of all, let's see what we do in YODA. So these are the various blocks. So I'll draw a long blockchain. So suppose the CIT is put into this block. Now what has to happen is that various ES nodes are going to submit their solutions. Okay? And what we do in YODA, and maybe I didn't explain these fine details earlier, is that we have a commit and reveal scheme. So what is this commit and reveal? That so we said you have to submit S and R, right? So S is the let's say a hash of the state, and R changes from one round to the next. So this is what has to be submitted, and we were talking about freeloading attack and so on. So we said that we deliberately choose this R so that it changes from one round to the next, and because of that, members of one ES are not going to be able to copy the solutions submitted in the previous round, right? But if you think about it a little bit, different ES members are submitting solutions in real time, right? And there has to be a window of submission. So somebody might do a freeloading attack on the submissions in his own round. Why does he have to look at the previous round? right? He can see what R is being submitted by other people in this round, and he just copies that. He's lazy and he sees that 90% of people have submitted a particular value of R, so I will also submit that. And that defeats the whole purpose. So it's a freeloading attack but done on the same round. So what we have is a commit and reveal. So what this means is that you don't submit this immediately. You submit a commitment, which is some sort of a hash, right? So you can hash this with some random information, and that is a commitment. So let's say some ES member, let's say he commits hash of, let's say, this tuple, right? And he let's say puts some random number here. And of course it could include his public key or something like that, right? Maybe you have also his public key depending on the requirements, right? But anyway, this should be, let's say, different for different ES members. So this is actually put on the blockchain initially. It's not the actual value. So there is some window in which this is done. And we are going to call that WSRC, and SRC stands for storage root commitment. Okay, so you submit this, and so different ES members are of course going to submit different commitments. I mean, so it's hard for any one particular member to copy from the others, right? And also what we have is that each ES member should keep his identity. He shouldn't let's say reveal that he is part of the ES. That has to be kept somewhat secret, you know, and that could prevent certain types of attacks, right? But anyway, we won't go into that in any detail, right? There are too many details which we've skipped over, right? I haven't described all of them. So let's say that they commit this information here, and so each of them cannot really see what the other has committed, right? So if some particular ES member I somehow tries to privately reveal this information to somebody else, then he can be punished. There is a scheme for it, right? So before a certain deadline, if somebody can prove what this ES member has committed, suppose he provides this and this, then the deposit of the ES member will be confiscated. Okay, that is what is done in YODA. Anyway, so because of that, we ensure that any particular ES member does this commitment, and then he keeps quiet about this because he doesn't want to lose his deposit. Okay. Then what we have is we have another period which we call a buffer period. Between this deadline and here there is another window period where you actually reveal what you had committed here. So this is what I call the storage root. Okay, so of course it is a storage root plus this other value R, which changes from one round to the next. Okay, so we have another window and another deadline in order to actually reveal what you had committed here. So the voting has to be finished here. So all ES members, they can't do any freeloading based on other people's commitments because they don't know what they have committed. They do the computation themselves and submit it. Then we have a buffer period where these ES members don't submit anything in particular, but there's another window period in which they have to reveal what they had committed. So they reveal, so each person is going to reveal this. So ES member I reveals this, right? Okay. And after this, of course, the miners are going to be able to do the counting, and to run the miracle algorithm and so on, right? They can easily do that because they can see what the commitments are over. Okay? So, of course, in our experiments, we wanted to see how big should this WSRC be, what should this WSR be, and so on, right? Because if you think about it, it depends on so many different factors. What if there is a lot of congestion in the network? What if there is no space in the blocks, to include commitments and, the storage routes and so on? How much should this be, right? It would depend on so many factors. But why do we have this this buffer period, where neither is there any commitment put nor storage route? There's sort of a gap that we leave here. So let's talk about that a little bit. And the reason is that what the students figured out is that all through our theory and so on, we have been assuming a single blockchain. Right? We've never talked about forks in the blockchain, but in reality, those things are possible. It is possible for a fork to be formed either naturally because of network delays, or it could be deliberately done by an attacker. Right? So what we said is that if the storage route is revealed before this deadline, so I would just call this so this is okay, so we are saying that SR must be revealed after this particular time. Okay. So why not have this W buff equal to 0? And and the reason is that there could be forks and somebody could perform an attack. So what does this particular deadline means? It means that if at this position in the chain, okay, so this is a particular block number, if somebody reveals what he has stored, what his commitment is before this deadline, then he is punished. His deposit is confiscated. So let me just call this, let's call this deadline 1 and this is deadline 2 and so on, right? So if ES member I, so we are only focusing on a single round, okay? We have one particular execution set. So if ES member I reveals what he has committed, before D2, then anyone can publish it on the blockchain, So I'll just note down here D1 and D2 are heights of the blocks. Okay, so it's not a time instant, right? In a blockchain, you would indicate a deadline by saying block at depth 1000 or 10,000 or whatever it is. So if anyone can publish it before D2 on the blockchain and confiscate his deposit. Right, so that's to prevent a freeloading attack to take place within that same round. Okay, so suppose D1 is equal to D2. Okay, so D1 is the deadline to submit your commitment, right? And D2 is the deadline. D2 is some marker that SR can be revealed after that. Okay, so suppose D1 is equal to D2, what can go wrong? And let's say this is D1 and somebody has put his commitment here. And suppose that D2 is also the same as D1 and he reveals his commitment here. So he reveals his storage root. So this is what has happened in the same blockchain. Now what does an attacker do? An attacker is going to create his own chain. Let's say he creates his own chain which is going from here and he includes this commitment. He puts the commitment here and he reveals the storage root, let's say here, right? Because see, he is doing this is all done privately. Okay, so he sees what is going on the main chain and he puts this storage root before D1 in his own chain and he confiscates the deposit of the that particular execution set member. So I should just say these commitments are off and this revelation of SR are for a particular ES member I. Right? And what the attacker does is, let's say he's able to create a longer chain and then the main chain, the public chain, and then he kills this one. So this chain gets orphaned. So of course this will happen with a smaller probability but non-zero probability, right? So somebody could perform this sort of an attack, right? And it's not too hard to do because let's say that this D2 is equal to D1 and let's say the attacker is forking. He may be forking even from just this one block ahead of the commitment. Right, so this main chain has just become 2 blocks long and this attacker has to get 3 blocks and so that may not be too hard to do in practice, even if he has, let's say, 10% or 20% of the hashing power. Right? Maybe the chances of success are fairly high. Okay. So this is a problem. This is an attack that though we have deadlines in the main chain, somebody could perform an attack with a private chain in which he steals information from the main chain and puts that information earlier in his own chain, so that it appears that this ES member has revealed his commitment too early, right? And the rules would permit the deposit to be confiscated. So what do we do? That is why we have this buffer period. We force D2 to be much larger than D1. Okay, so that this sort of a private chain attack becomes harder. Okay, because if let's say D2 is 10 blocks ahead of D1, then the attacker would have to win this private chain attack on a chain in the main chain which is fairly long. At least it may be 11-12 blocks long at least by the time this information is revealed, and it would be very hard for an attacker to generate a chain which is longer than the main chain. Okay. So that's the idea over here. So let me just write that out over here. So we have D1 here and we have D2 larger than D1, so that a private chain attack is going to be harder. Okay. Let's say this is a long chain, so the private chain attack is harder on a longer chain. So the attacker would have to create a chain privately which is longer than this chain, and after this, and it's non-trivial because after this is revealed over here, now he has to put this information in some block over here, right? So he can't even create this block immediately. He has to start his private chain attack after this information is revealed here. So he's already behind by, let's say, 10 blocks. If this W buff is 10, he's already behind by 10 blocks, and now he has to catch up and overtake this chain, which is going to be very hard to do, right? So that's why this W buff is non-zero. Okay. So taking this into account and so on, what did we do in the experiments? So here are some details of the experiments we did. So we had the size of the stake pool equal to 1600 nodes. Okay. And what we were doing is we wanted to study what should WSRC be. So how much time do you need to actually submit the commitments? And what we were doing is that we ran this experiment in our test bed with this many nodes, and we had the size of the execution set to be 40. Okay. And what we wanted to do is to vary the gas size of the CIT. Okay. And I'll just show you the result that we got. So what I'm plotting here is the time in seconds. So we should note that inter-arrival time of Ethereum is roughly 15 seconds. So you'll find this graph in the paper too. So this is the CIT gas usage. So we had, this is on a log scale, 10 to the power of 6, 10 to the power of 7 and so on. Okay, and of course this is multiplied by 5.3. So why this 5.3? Well, because really the block gas limit is essentially roughly equal to 5.3 times 10 to the power of 5 gas per second. So this is the Ethereum limit. Right? So we just wanted to have this as a reference, right? So effectively sort of what, suppose I have 10 to the power of 5 here, right? So this would be the Ethereum block gas limit, and we want to see what happens. Suppose I make the CIT equal to, let's say, 10 times or 100 times the block gas limit. What happens? Okay, and of course this is going to be run off chain using the YODA protocol. Okay. Let's see. So when we had this equal to the block gas limit, we set WSRC equal to 4 blocks. So this is WSRC. So this was, we chose it, and we set WBuff to be hardly a couple of blocks, and WSR we set something to be this. Okay. So what should we expect to happen over here? And we looked at what is the average time taken to submit all the solutions, all the commitments, and roughly it took about 20 seconds. Okay, so within a block pretty much everybody was able to submit a solution within a block or two. Right? Everybody was able to submit their commitment. That's what we found, and of course the deadline was a little bit larger than that. We set it to 4 blocks. Okay, and so what's going to happen? So this CIT is computed off chain, right? So suppose the CIT appears in one block. Suppose the CIT appears here, and the time between blocks is let's say 15 seconds. Okay. And remember what we said earlier, the entire Ethereum block is pretty much computed within 1% of this time, right? We said that the validation time is hardly 150 milliseconds. So this corresponds to this limit, Ethereum gas limit corresponds to about 150 milliseconds of the computation time of a typical CPU, right? So even if we have the CIT computation time 10 times that, so that's 0.15 seconds, right? Corresponds to this time of CPU computation. So even if you make it 10 times, it's going to be 1.5 seconds. So within 1.5 seconds, people are able to compute. right? So they are able to submit the commitment even in the next block, which is what we see here, right? And maybe if there is no space in this block, some of the commitments may show up in the next block, right? So that's not a big deal, and we noticed that indeed the time taken to submit so this is the average time to submit a commitment. So this WSRC is the limit that we set, a deadline, and everybody is comfortably able to submit within that time, right? And even if we make it 100 times, that would be okay. It's not such a big problem, right? But as we increase, okay, clearly the time taken to submit goes up, right? And I think as we go to 10 to the power of 10, the time taken to submit goes up much higher. Okay. So this 0.15 seconds is what we have seen in like a worst case, but so this may be a typical gas per second which is allowed roughly anyway. But what we see is that as the CIT gas usage goes up, the time to compute should also be included in the WSRC. It is not just that they do the computation immediately and they can submit their commitment. They need to be given enough time for that, right? So here we had to increase the WSRC to be much higher. We had to make it 120 seconds over here. And of course W buff and WSR also were increased. Okay, so this 0.15 seconds, of course I am using from some other paper whose information I had. Actually have to look in the YODA paper to see exactly how much time this would take, right? And maybe this could be done in even less than 150 milliseconds on a typical CPU. Okay. So we don't, so here of course we would say that we need maybe 2 blocks or so, right, or 3 blocks to submit. But definitely when we go to 10 to the power of 10, we need many more blocks for this computation to be done. Okay. So depending, the lesson we learned from here is that depending on the CIT gas usage, you would have to set your deadline appropriately. So this of course assumed that there weren't too many other transactions going on. If there was a lot of congestion in the network, a lot of Ethereum transactions being submitted, these commitments would be competing with those for space in the block. And again, in that particular case, we might need to increase this WSRC appropriately. So another experiment that we did is to look at when there are multiple CITs being computed by different execution sets. So I'll just summarize the previous one. So the lesson is depending on CIT gas, set WSRC deadline let's say window appropriately. Okay, so the larger the CIT gas, the larger should the WSRC. So what if you have multiple CITs competing. So I'm going to show this same graph. I'm not going to show the WSRC limit and so on. This is the, I'm going to show the average time to submit a commitment. What happens over here? So average time to submit and this is in seconds. And here on this axis I am going to show the number of let's say simultaneous CITs being computed. Okay, and okay, so the question is, what do we see over here? So let's say this is 20, roughly one block interval for 30. Let's say this is 10, 20, 30. So in this particular experiment, essentially the results are valid for either 10 power of 6 as being the gas or 10 power of 7, right, multiplied by this constant factor. For either of these, we would have the same result for multiple parallel CIT computation. So of course, for this particular, let me write that down. Let's say the gas times 10 to the power of 6, right? So, or it would work for 5.3 times 10 to the power of 7 also, okay, in that particular range. So when we submit a single CIT, we do a single CIT, no parallel computation, okay. So then it takes roughly 20 seconds in order to submit the solution. Okay, that's what we've seen earlier from the previous result. But YODA can have multiple CITs running in parallel, right? So every time we run a CIT, we just choose a random execution set from the state pool and we do the computation, right? So you can have two different execution sets, right? Probably there may not be any overlap between the two of them, and you can compute those CITs in parallel. So that would increase the throughput of number of CITs being computed, but how long does it take to submit a solution? And we saw that when we go to 2 and 4 and so on, right? So here we have an exponential increase. This is a log scale. What would happen, and normally one might think that it shouldn't affect much, because after all they are they're doing the computation in parallel, and if the execution sets don't intersect, then why should it matter? You know, I mean, everybody can do the computation within the deadline. I mean, you know, within a single block for this particular low gas usage, you could be able to do it. But it turns out to be non-trivial, and in fact we found that this goes up. So why should it take more time for the execution set members to submit their solution? Okay, so, and you might realize that it actually has to do with the size of blocks. So Ethereum block size can only accommodate a certain number of transactions. It's not of infinite size. So we are submitting our execution set is of size 40 here, right? So that means 40 different people have to submit commitments for each CIT. So when you have 16 CITs running in parallel, that means this number has to be multiplied by 16. You have that many transactions. So it might take several blocks to accommodate all the transactions. So, right? So for this particular instance, this particular experiment, you need 16 times 40 commitments should be submitted to the blockchain. Right, and so this would need more than one block. Which is why even if the computation is done earlier, the bottleneck becomes the blockchain space, okay, because of which it takes some time to submit the transactions. Right, so these are some of the things we learned from our experiments, and definitely it gave us more insight, right, and it gives people more confidence that this whole idea is going to work, and when what particular parameter values to choose for the WSRC window and so on, right? So this was all that I wanted to discuss about YODA. It was really a loaded paper, and somebody who read it, a senior professor from NUS Singapore, in fact, told us that we should have written it as 3 papers because there were too many new ideas, right? And that's the reason it's taken me this many lectures to explain YODA, because it's probably equal to normally what you would find in 2 or 3 papers, right? But we will continue our discussion on scalability of computation in the next class, right? But we'll move on beyond YODA.